Okay, gang. Well, welcome to CSC 475, Artificial Intelligence. We're getting close to being at midterm. Our midterm exam is on Tuesday. I've now talked with 3 of you about COVID accommodations. So there are 3 of you that I'll be giving the exam online with. There's 1 of you that I'll be sending an exam to occupational, TDS, Testing Disability Services. Okay, any questions before we get started? Any questions before we get started? Okay, I will say that internet's been terrible here today, so if we lose it, well, we lose it. But we can keep going by phone. Okay, so like I said, the exam will be on Tuesday. Let's pick up where we left off last time. I had been talking about the backpropagation equations, and so we had started with this, which is a visualization of the backpropagation equations for sigmoid neurons, and basically our equation for the bias gradients in the last level. That's what that capital L means, the last level. So bias gradient for node J in the last level capital L, is just the output of that node J minus the desired output for that node J. So the difference between what it gives you and what you want, right, for that node, times the output of that node times 1 minus the output of that node. So that's the error, the bias gradient for the, in this case, the jth node of the last level, level 4 here. So that's one equation. The next equation is, okay, well, what about biases for nodes that are not in the last level? Well, basically, that's the weighted sum of the bias gradients that connect to that node, times the output of the node times 1 minus the output of the node when we're talking about sigmoidal neurons. So again, let's look at it. We've got this node, and we want to figure out what its error is, what its bias gradient is. Well, we look at the weights that connect that node to all of the nodes in the next level, and we look at their errors, their bias gradients, okay? And so we take the weighted sum of those bias gradients, the weight times this one, plus the weight times this one, plus the weight times this one. And so we get a weighted sum of the bias gradients. And we're doing that because essentially we've got these errors, right? And we want to figure out what the error is here. Well, this weight kind of tells us how much this error contributes to the error in this node. And this weight here tells us how much this error contributes to this weight, etc. So basically, if this is a very, very weak weight here, even if you have a big error here, because it's so weakly weighted, this guy really isn't contributing to that. That error really doesn't contribute very much to this error here as we work our way backwards. So again, it's the weighted sum of the bias gradients times the output of this node times 1 minus the output of this node. Now, if you look at these subscripts, and it's easy to get lost in the subscripts, but don't, right? We're talking about the bias gradient for node K in this case in level 3, level L. So we're looking at the weights in level 4. The weights that connect level 3 and level 4 are the level 4 weights. So that's why that's an L plus 1. So if this were 3, that would be 4, right? the bias gradient in level 4 sub j. Well, what's this WJK? Remember, the J is the node you're going to, and the K is the node you're coming from. So we're interested in node K here, so we're not summing over K's, we're summing over J's here. So from K to J, from K to the next J, from K to the next J. So if you look at it and think about it, the J's would go like 1 or 0, 1, 2. We're changing the row number here. And so if we look, right, it's the row numbers that are changing. And so this is, if you think about the weights here being in a two-dimensional matrix, okay, when we were computing forward passes, right, we would go the weights across a row down a column of biases. But here, we're backing things up and we're going really down a column of this weight matrix. So if you were going to look at this in matrix form, and I'll show you in a little while, you would actually have to have a little transpose on the matrix, because if this is a column matrix, you can't multiply a column matrix times a column matrix, right? You've got to have like a row times a column. So you can't have a column times a column. So if we're doing this in matrix notation, as you'll see in a minute, there'd be a little transpose on that. But that just means I've got a row, and I've got a column, and I've got a column, and so I've got to flip one column on its, my hand is going away, one column on its side so that I can do the matrix multiplications properly. Okay, so that's the equations for the bias gradients at the intermediate layers. And then the last equation we have is, how do I come up with a bias gradient for a weight? Well, that's just going to be the output times the bias gradient. So the output of the source node times the bias gradient of the target node. We're going from here to here. So the output here times the error here will give me the weight gradient for this weight here. So it's very simple. Okay. I promised you that we would look at a deeper understanding of these equations and where they come from, and we will do that here in a moment. But before we do that, I wanted to go back and revisit the Excel spreadsheet that we briefly talked about last time. The thing is that I've given you a spreadsheet that unwinds the loops, essentially, of your program. But this spreadsheet has every equation in it, okay, for a very small network with a little bit of data, training data. And I've done this so that when you're writing your program, this is a 4 by 3 by 2 network. So 4 nodes in the first level, 3 nodes in the second level, and 2 nodes in the final level. You can just, as you're writing your program, you can just set those as, since it's a 3-layer network, instead of 784 times 30 times 10, you can just set it to 4 by 3 by 2. And if you do that and use the exact same random numbers that I've come with as your initial weights, and use the exact inputs that I'm giving you here and the exact learning rate, the numbers that your program generates should exactly match the numbers in this spreadsheet. So this will be a way for you to check your equations and make sure that that the math works. So if you verify that all of your computations are correct using the spreadsheet, then you change it to 784 by 30 by 10. And now you know that at least the computational part of your network is correct. So that'll make debugging tons easier, okay? So let's look at this spreadsheet. Now I've got it zoomed way out, right, to begin with. Of course, you can't see the numbers, but I wanted you to get a feel for the overall shape of this thing before I launch into you know, what the various equations are. The first thing is over here in the upper left-hand corner is where I have my inputs and my outputs. I have my training data, and we'll go and we'll look at this in a little while. This is where I have the network parameters, like how many nodes per level and what my learning rate is and stuff like that. And then each of these big things here is an epoch. So this are the epochs unwound, right? This would be your sort of your outer loop, right, in your training routine. And then within each epoch, you have 2 mini batches. There are 4 inputs to this network, and those 4 inputs. This one represents running 1 input. This represents running a second input, a third input, and a fourth input. But I have them broken into 2 mini batches of 2 each, just so that I can show you mini batches and how those work. And so, what each of these things down in the mini batches are doing is there's some work here, and then there's some work here. This represents a forward pass where you're taking in an input and driving it through the network, and then this is the back propagation where you're computing your gradients, and that's on one input, and then you take a second input and you pass it through the network and compute the error gradients. And then the next thing you do at the end of that little mini batch is to update your weights, and that's what we'll be doing here. With those updated weights, they'll plug in here. You will then run the third input and back propagate that third input, and then a fourth input and back propagate that fourth input, and then you'll calculate the updated weights and biases for at the end of the second mini batch. Well, since there's only 2 mini batches, that finished you with epoch 1, and then you go and you start the second epoch, and it has its 2 mini batches: forward pass, backwards pass, second item, forward pass, backwards pass, update the weights and biases, third input, forward pass, backwards pass, fourth input, forward pass, then backwards pass, etc. And you do this epoch after epoch, right, until your network learns what we're trying to teach it. So let's start to go back to normal view here. I can actually see this. Actually, I think I have it set where you can still view it if I go to 70%, I think is what I tried. You can still see the numbers, but it gives us a little bit bigger view. So we start out with our training data. We have 4 inputs, right, and are broken into our 2 mini batches. The first input is 0, 1, 0, 1, and the output should be 0, 1. And the second one is 1, 0, 1, 0 with an output of 1, 0. And then the third one is 0, 0, 1, 1 with an output of 1, and then 1, 1, 0, 0 with an output of 1, 0. So basically, if you look at it, what does this thing and this thing have in common? Well, when the last input is a 1, we want our second output to be a 1, right? And what does this one and this one have in common? Well, when our first input is a 1 and when our first input is a 1, we always want to generate a 1. So basically what we're hoping this thing will learn is it's got 4 inputs, and when the fourth input is a 1, we want our second output to be a 1. And when the first input is a 1, we want our first output to be a 1. So that's what we would hope that it would learn from this little bit of training data. Here are the network characteristics. There are 3 layers. There are 4 nodes in layer 1, because obviously you have 4 inputs, so there would be 4 nodes. The intermediate layer is only going to have 3 nodes in it, and the output layer will obviously have 2 nodes, because that's what our outputs are. Okay? So we take this 0, 1, 0, 1, here it is, 0, 1, 0, 1, and we feed forward that into our network. And here are all the equations for a forward pass. This is the input data, and so it goes in here, right? And here are the weights. These are green because they're randomly generated, okay? Our weights and our biases start out as random. As a side note, when I first created this network, this spreadsheet, and was trying to get the spreadsheet to work before I had ever written the program, I had just thrown 0.5 in as all of the weights and biases. I went, well, I don't know what they're supposed to be. They're supposed to be random. What if they were all 0.5? Interestingly, the network wouldn't learn. In fact, I didn't think about that. I thought that there was an error more likely in the way that I transcribed some of these equations, right? And I spent several hours debugging and could never find anything. And then I went, crap, well, you know, I know that neural networks aren't guaranteed to find, you know, their minima. And I didn't really use random weights and biases. So let me go back, and I used a little random number generator to generate random numbers between -1 and +1. And I just used it to generate a bunch of random numbers, and I plugged those in, and lo and behold, it started learning after that. So I was like, yep, it is important that your weights and biases originally be random, and it's also true that that there will be some inputs, some sets of weights and biases that'll just be set so that the network just won't learn. So anyway, so what are the equations here? So again, here are the weights, right, and the biases. So row 1 multiplied by bias 1 will give you the Z value, right? You can see row 1 times the input gives you the Z value for the first node. And then that Z value, I know the numbers are tiny here, but if you look at it, here I'm doing the multiplications, right? So this first part is the weighted sum plus J27, which is the bias. So that gives you the Z value, right? And then that Z value is plugged into, that Z value is plugged into our equation. 1 over 1 plus 2.7, blah, 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 that's E, right? To the, there's a little up caret, you can't really see it there, but raised to the minus L27 power, raised to the minus Z power. So that is right here is where I take this Z and I plug it into the sigmoid equation to get the output for level 1. And I do that over and over. So that's, again, the equation. That Z was the second row times the second row of weights times the biases, and the third one will just be the third row of weights times the biases. This is a very good way of helping you get a feel for actually seeing how these equations are working, right? Because I've told you it's a row times the, a row times the, I've told you that it's a weighted sum, a row times the column plus, this equation goes over this, plus the bias, right, gives you Z. So the weighted sum of the inputs plus the bias gives you the Z. And you can see it here graphically. Now you can't see the bias because I'm sitting on top of it, but you can see the weighted sum of the inputs, the row times the column. Okay, and then so this layer here of outputs becomes the inputs for the next layer. So this is 0.086, and actually if you click on it, you just see that I just copied it, right? It's just copied from here. And the next one will just be copied from there, and the next one will be copied from there. So this is just a copy of that, right? And it's going to work the same way. You'll have a row here times the inputs, so a row of weights times the inputs plus the associated bias will give you the Z, and there it is. And then you plug that Z into the sigmoid equation, and that'll give you the output there. Okay. So this is the forward pass. The input goes in, and you compute the activations. We also have the correct answer. Remember, this was the input. We also have the correct answer because I gave it to you in the training data. Here's the input, 0101, 0101, and here's the correct answer, 01. And you can see the correct answer down here, 01. That's going to let you calculate a cost function, which we don't directly use, and it'll also, the derivative of that cost function is going to let us calculate our errors. So these aren't weights and biases. These are weight gradients and bias gradients. Okay, the error here. But you're going to have a gradient for every bias and weight that you had. So the shape of these matrices are going to be the same. This is a 3 by 4 because this is a 3 by 4. So if you've got 3 by 4 weights, you're going to have 3 by 4 weight gradients in that level. And there they are. So how did we compute the weight gradients? Well, we went over this last time, and we just looked at the equations again. But to calculate the delta, actually these are the same thing. I really didn't need in the equations. Remember, we have 4 equations, but they reduced to 3 equations, and in the first version of the equations, we're just using a delta, a D, but this is the correct answer. These 2 columns are exactly the same. But anyway, if we want to look at the computation, right, you have the output minus the desired output, output minus desired output, times the output, times 1 minus the output. And that gives you that bias gradient. Same thing here for this guy. Its output minus its desired output times its output times 1 minus its output. It's right there. That's the equation that we just went over here. And if we if we look, well, what about the weight gradients? Well, remember the weight gradients are well, I guess you can't see it there. It's it's simply the output times the error. So remember, this is updating one weight, right? And so it's associating the output associated with that node with the bias associated with the destination, right? So it's the link between two levels, right? So it's the output of this node times the error that's in the destination node. And so you can see we looked at that one. You can look at this one. So it's just the next one, right? And then this one, and you can see it didn't jump like that, annoyingly. You could see that it's now the third one, right? So if I look at this one, it'll be the first output times this, the first output. Oh, Michael, you're driving me up the wall here. Sorry, skipping here. First output times the bias gradient. Second output times that bias gradient. Third output times that bias gradient. And so as I went down this column here, right, multiplying, I was able to get this row of bias gradients. Same thing here, right? Now it's first times the first bias gradient, second output times the bias gradient, etc. All right, and so that was one level. It'll do the same thing as we go up to the next level here. So, come on. So essentially, every single equation, all three of those equations applied to every node and every bias in the entire network is here. Once you've gone through both passes, right, training case 1 and training case 2, you will now have, these are the training case 2 gradients, but we also have the training case 1 gradients, and then you just put them together, right, to get the updated biases and weights. So these won't be gradients anymore. These are biases and weights, right? So remember the formula for that. The old bias, right, minus I'm losing it here. Minus the learning rate divided by 2, which is the number of items in the mini batch, times the 2 gradients that you've computed, right? And that'll give you how to update the biases, and you'll do exactly the same thing with the weights. And so now we have updated biases and weights. So if you look here as we begin the second mini batch, this is 0.1511 with a negative. In fact, I just copied it. That's all I did. All right. So these are just those things that we just computed, copied over, because we've now updated our weights and biases, and we use those as we process mini batch 2. So the forward pass, the backwards pass. Now we're going to do example 3. It's forward pass, it's backwards pass. Now we've reached the end of that, so we update the weights and biases again. And that ends epoch 1. We would then go down and start doing the next epoch. So 1, 2, 3, and we just keep going down 4, 5, where each of these epochs have too many batches in them. So study. My advice is, if you go, well, I'm kind of lost in these subscriptions, study this spreadsheet. I built it for you so that you can study it, so that you can see every equation lined out, okay? And the equations combined with the spreadsheet, combined with the pseudocode for the algorithms that I gave you for backpropagation and gradient descent, you have absolutely everything you need to implement the program, okay? You have way, way, way more to start with than I had when I first tried to write a program to do this, okay? Are there any questions before we continue? Are there any questions before we continue? Will we discuss batches today? You mean the mini batches? I consider that we've already discussed them. Essentially, if you go back to the algorithm for stochastic gradient descent, I think that was maybe 2 lectures ago now, so a week ago, you know, if you're using stochastic gradient descent, step 1 is you randomize all of your inputs. Step 2 is you break them into pieces. So for your data, you'll have 60,000 inputs, and you'll break them into 6,000 groups of 10 each. So you just randomize everything, and then you go through grabbing them 10 at a time. That's what you got to do. So that's all I had on batches. There's not a lot to talk about. If you still have questions about it, I'll be happy to try to answer them after class. Again, I don't think that there's really that much there to talk about. Just go back and look at the pseudocode that I gave you for stochastic gradient descent and backpropagation. I gave you the pseudocode for that. We then talked in detail about the calculations, and we're going to talk about them even more, for stochastic gradient descent, for backpropagation, the 3 equations, right? And now I've given you a spreadsheet that has a real world. This spreadsheet actually teaches the neural network actually learns, and we can see that because if you go and you look at the output of it, right? When we've done no training at all, when we begin, okay, we gave it 0, 1, 0, 1, and we wanted it to end up with a 0 followed by a 1. That's what the output is supposed to be. Well, what was the output to begin with? Let me make this just a tiny bit larger. What was the output? Well, the output, as you might expect, because we haven't trained anything, is that it said, well, I'm 68% sure that the first thing, and I'm 0.539, so basically 0.54, that is the second thing. So basically, it's assigning values that are random. Okay, so that's after the very first mini batch in epoch 1. Now it's just easier as I go. This is the second epoch, so this is after now it's done 2 training cycles, and we're giving it the same thing, 0, 1, 0, 1. And I want 1, 0, right? Well, now they've changed a little bit, but not much. The cost function is still 22%. So how about after 6 training examples? Well, this one now is below 5, or 0.5. This is below a half now, and this one is above a half. Well, that's still a far cry from 0, 1. But as I come here and I look, okay, now this is getting a little smaller, and this one's getting a little larger. All right, and so now then the next epoch, this is a 0.3 and this is a 0.7. And usually the way you do this, so the cost function now is 10%. And normally the way you interpret an output like this is you just say, if only one of them is supposed to be a 1, you say, okay, take the greatest, set it to be a 1, let the rest of them be 0. So you would be getting proper output here, right, matching what we wanted, but you're still fairly far away. Sometimes we look at these and we go, if it's below 0.5, we give it a 0. If it's above 0.5, we give it a 1. So even that way, we'd still be giving us a correct answer. But there's still a lot of error in there. But you go a little further, this is now less than 0.3, this is 0.78, and I think that's where I stop. But you see that each time I do one of these epochs, this gets closer and closer to the correct answer. It would be giving you it would be trained essentially if you took the largest one as a 1 and the smallest one is 0. So it learned the outputs. Well, it learned to recognize that input. What about the other inputs? Well, here is the second input, which is supposed to be a 1, 0.68, 0.23. Clearly that one's bigger, so it's giving you a 1 here. So it worked right on the first and second inputs. How about the third input? Well, same thing, 0.23, 0.82, it's supposed to be 0, 1, so that's correct. And this last one will be correct too, 0.68, 0.21. So clearly this one is much larger than this one, right? So 1, 0. So it did learn. The spreadsheet implemented the learning algorithm, and you can see that it learned over time as we went through the various epochs, even though when it started, it was terrible, right? Because it just was guessing, and its first guesses were terrible. Both of these were over 0.5, and actually this one was bigger than this one. So it was completely wrong when it started, as you would imagine, because it just had random values in it. Okay? So it learned. And the spreadsheet absolutely lays out exactly what you need to do. Okay. All right, so that was our spreadsheet. So let's see, what's next? Okay, well, what I wanted to do next was I wanted to try to talk more about these equations. We're kind of going into a phase here where I want to do 3 things. I want to show you, give you a little bit better understanding of the math behind these equations. I'm not a mathematician. I'm terrible at math. It's been decades since I've had calculus, so you're going to have to cut me a little bit of slack. But even with that, it's pretty clear what's going on here. Okay, so I'm going to do that. We're going to go through the math. We're going to try to show you where those final equations that we've covered, where they come from, in a sense. Okay. I'm also going to show a different activation function, a ReLU, and I'm going to talk about how that changes the equations. And then I plan on showing you guys 2 videos from YouTube. Each one is about 10 minutes long that really go through the math behind where the equations come from. The YouTube video does a much better job than I would ever be able to do it. It's got pretty graphics, and it's a lot. It's just nicely done. So we're going to do that. I'm going to do the equation, go back to the original equations, show you where the version of the equations that we've covered come from. I'll then look at a different activation function, the ReLU, show you how that changes the equations, and then we'll go through two videos that show you sort of the calculus that underlies these equations. And after we finish that, my plan is to show you a few more activation functions and talk about the advantages and disadvantages of those activation functions. So that's sort of a plan for the rest of the lecture here. Okay, so let's get started with that. Okay. Here is the actual equation as it's normally written for the for computing the error in the final layer of the network. So remember, we have three basic equations. We have an equation for computing the error in the final layer, the bias gradients for the nodes in the final layer. We then have an equation for computing the bias gradients in the intermediate layers or the non-final layers. And then we have an equation for computing the bias gradients for weights. Those are the three equations that we have. So this equation is normally written like this. So basically, the error, and this equation is written from the point of view of a particular node and a particular layer. So the error in node J of level capital L, using the capital means this is the last layer, okay? So the error in a node J in the last layer is the derivative of the cost function with respect to the output of that node in that layer times the derivative of our activation function. In this case, our activation function is sigma. So the little prime there, sigma prime, is saying the derivative of the sigma function. It still takes in, our z like normal. Okay, so again, this is the equation for the error in the jth node of the lth final level of the network. And so, as I said, A sub j with the superscript of capital L is the output of the jth node in the lth level. The z is just the weighted inputs, right? So the weights times the inputs plus the biases, right? And that's our z, right? And we stick z into the sigmoid function to give us an activation, right? Our sigmoid function is still defined like it's been defined since we first introduced it, all right? 1 over 1 plus e to the minus z, where z for node J in level L is the weighted sum of the inputs plus the bias, right? And so that'll give you the output for a single node for node J in level L. You put a prime there, that's just the derivative of that function. What about C? Well, we haven't really talked about C before. C is the cost, and if you notice, I did show a cost value in my spreadsheet just so you would see that it's there. So what is the cost function? Well, generally, there are different ways of computing costs, but generally, costs are or error can be computed where you've got two quantities. You've got your actual output and you've got your desired output. And you look at the difference between those two things. So you can write it as the desired output minus the actual output, or you can write it as the actual output minus the desired output. You might notice, well, depending on the order that I put these things, it's going to flip the sign, right? The other thing you might notice is I'm summing up the errors. Well, if I'm summing up errors, but they've got signs on them, that's going to cancel things out, and I don't want that to happen. What I'm trying to figure out is, let's say here's my answer, okay? My desired answer, but I get an answer here. Maybe we consider that to be a positive range. And then the next answer I get here, okay? So that's negative. Well, if I added those two together, it would shrink the error, but that's not what I want. I want to know, okay, this one moved me this far away, this one moved me this far away. I'm kind of keeping up with how far away was each of the answer from what I wanted the answer to be, okay? So it's the distances that I'm interested in, not the directional signs so much, because I'm interested in the total error. So one simple mathematical way of fixing that is if you square it. So people talk about, you know, the square error or the mean squared error. And that's because if you take this quantity and you square it, it doesn't matter if it was a positive or a negative, it's going to end up being a positive, right? Positive is positive, negative is positive. So it'll counteract that. And also a nice thing about squaring it is it doesn't matter if you go what I want minus what I got, or what I got minus what I want. It's the difference between those things. By squaring it, the order that you did them doesn't matter. Now, sometimes on a cost function, you'll see a 1/2 thrown in front of it. In other times, you won't see a 1/2 thrown in front of it. I have it written this way because Chapter 2 of Nelson, the book that you should be looking at, I've given you the link to it. It's in the notes. It's where this comes from. You should read Chapter 1 and 2 because I've kept my equations so that they match Michael Nelson's book, right? So he uses a 1/2, so I'm using a 1/2 here. The nice thing about that is when you take the derivative, as we'll show in just a second, if you have a 1/2 in the formula, what happens is a constant will go away. If you don't have a 1/2, you'll end up with a constant of 2 in front of your formula, and it won't matter. It's just a constant, and it just shifts things a little bit. But remember, you're jiggling thousands of weights and thousands of biases, so having a 2 in front of something makes absolutely zero difference in the grand scheme of things. It's just a little simpler if there's not that constant 2 floating there. So that's why some people will do their cost function by putting a 1/2 in front of it. Okay, so that's our cost function. We're going to take the derivative of that cost function. Because of the square, the equation can be written either with the y first followed by the a, or the a first followed by the y. Now, what happens when we take the derivative of that cost function with respect to the output a? So we're taking the derivative of this function with respect to a. And what happens is the 2 comes down in front, right? And this gets reduced by 1. So the exponent essentially goes from a 2 to a 1. So the exponent goes away, and you get a 2 here. So 1/2 of 2, that becomes 1, so it goes away. And lo and behold, the derivative of the cost function ends up being what's my output minus what's my desired output. So that's where that output minus desired output comes from. It comes from being the derivative of the cost function with respect to the output. Does that make sense? So that's the first part of this equation here, right? This is just the derivative of the cost function. and that exists both in whenever you're when you're computing your error, right? And you can only use this in the final layer, because only in the final layer do we have the desired output. We've got both the generated output and the desired output. Okay, so this comes from the derivation of the cost function with respect to the output. What about all this other mess here? And interestingly, you see that same mess there and here. You see that exact same mathematical phrase. Well, where does that come from? Well, if we go back and we look at the equation, that is going to be the derivative of the sigmoid function. Okay, so the derivative of the sigmoid function should come out to be the output of the sigmoid times 1 minus the output of the sigmoid. Okay, and these two parts, the derivative of the cost function with respect to the output and the derivative of the cost function, together give you the bias gradient for that node. Okay. For those of you who have forgotten calculus like I have, you might say, Mike, won't I get a different answer if I leave the y before the a rather than putting the y after the a? I mean, wouldn't one of them give me a minus y and the other one give me y minus a? No, in fact, that doesn't happen because of the fact that we're getting the derivative of the cost function with respect to the output. I went, and I had forgotten the details of that, but I went to Wolfram Alpha and I plugged it in, and when you take the derivative, it'll reverse it. So this will always be the derivative of this function, regardless of if you wrote the original function this way or you wrote the original function this way. So this will always be the derivative of that function. Okay? So that's real cool. So now we know that where that output minus desired output comes from. It is the derivative of the cost function with respect to the output. And remember, derivatives are like rates of change, right? And that's really what we're getting with these bias gradients. We're getting the rate of change, how rapidly that error is increasing, how rapidly that cost is increasing. Because that's what we want to know, because we want to move in the opposite direction of that gradient, right? To decrease that cost. So that was that. I do make a note here in the videos that we're going to show by 3 blue, 1 brown. He does not put a 1/2 in front. So because he doesn't put a 1/2 in front, he's going to write the derivative of the cost function with a 2 in front of it. Offsetting these things by a constant, especially a small constant, is not going to make any difference whatsoever in the end. And so you will see some sources that would have a 2 there. You'll see others that don't have a 2, and you ask yourself, well, how did that happen? It's just he used a slightly different cost function than Nelson used in his book. Nelson put a 1/2 in front of it. I've forgotten the author's name of the 3 blue, 1 brown, didn't put a 1/2 in front of it. So that's why he ended up with a 2 in front of his derivative. Okay, so what's the derivative of the sigmoid? Well, I can give you most of it. Here is a showing the derivative. Okay. Now in this, y, which is the output, is the output of the sigmoid function, and dy dz is the derivative of this function here. So first off, y equals 1 over 1 plus e to the minus z. Another way of writing that is 1 plus e to the minus z to the minus 1. Minus 1 is just 1 over that. So this is showing this algebraic equivalence here. The next thing says is, okay, the derivative is this. Well, that depends on calculus, and I've forgotten why that's the case. But we will take as gospel that if you take this function and you take its derivative, you'll end up with 1 times minus e to the minus z over 1 plus e to the minus z squared. Okay, so take that on math gods. Okay, but you might say, well, this is a far cry from output times 1 minus output. That's true, but with a little bit of algebraic trickery, we can get it to where we need to be. Because if you look at this thing, you can rewrite this as 1 over 1 plus e to the minus z times e to the minus z over 1 plus e to the minus z, right? All I did was take this. This is just this twice. So I'm multiplying here. That gives twice. And this is just minus 1 times minus e to the minus z. You might say, well, where did my minuses go? A minus times a minus, a negative times a negative is a positive, so they cancel out. So it's just easier to write it as 1 over 1 plus e to the minus z times e minus e to the minus z over 1 plus e to the minus z. Okay, great. Well, what is 1 over 1 plus e to the minus z? Well, I defined that here as the output of the function, right? So this is just y. This is just the sigmoid function, right? So that's where the y comes from. And what about this 1 minus y? Well, this can be transformed into 1 minus y. How? Well, start with what we've got here, and you might say it's silly to do so, but you can add 1 and subtract 1, and that's not going to change the quantity here, right? So if this is e to the minus z, if I add 1 to it and then I subtract 1 from it, I still have e to the minus z. But by doing this little bit of silliness here, right, I can break this now into 2 parts. I can break it into 1 plus e to the minus z over 1 plus e to the minus z plus minus 1 over 1 plus e to the minus z. So I broke this. First I took this, I added a 1 and subtracted a 1, which allowed me to break this into 2 pieces. And if I look at this, what is 1 plus e to the minus z over 1 plus e to the minus z? That's a 1, right? So that's where the 1 comes from, plus minus 1 over this. Well, this is just minus y, right? So this whole thing is 1 minus y. This whole thing is y. So the whole thing, the derivative of this function, is this monstrosity that simplifies down into output of the function times 1 minus the output of the function. That's where that came from. So putting it all together here, you can think of the derivative of the error in the in node J as being, okay, the derivative of the cost function with respect to the output of that node times the derivative of the activation function. So I just color-coded it blue and green here. We've already shown that the derivative of the cost function with respect to the output is what I got minus what I wanted, right? So you can translate this into, okay, just replace this with its value there, what I got minus what I wanted, times the output of the sigmoid function, and we just showed that the output of the sigmoid function is output times 1 minus output. Well, what is our output, right? Our output is the activation of the node. So from this intermediate step, we come down here and we get, okay, the error in node J in level, the last level, capital L, is what did it produce minus what did you want times what did it produce times 1 minus what it produced. So that's the whole process from soup to nuts, with the one exception that you're going to have to take on faith that this is the derivative of this function if you don't remember how to do it from calculus. But that's how we got this, okay? So what about well, one other little thing. I'm showing this for node J in level L, right? And normally what we do, the way we use this in our program, is we're going to loop through each of the nodes in that level, right, to compute this. So we're not just going to be interested in one node, right? We would have to do it for node 0, for node 1, for node 2, for each of the nodes in the layer. That's fine. And that's how you're going to do it in your program. But most neural networks these days are run on either graphics processing units or tensor processing units. And that hardware allows you to do lots of things in parallel. So basically, you can do matrix math where you do the whole matrix at a time. The different parts of the computations that we're doing sequentially would be done in parallel. And so, if you were doing this at more of a matrix level, well, you would be interested in not just node J in level L, but you would be interested in all of the gradients in level L. So this is a vector. So if there were, say, 5 different nodes in, or 10, let's say 10, it matches our programming assignment. Let's say there are 10 elements in the last level. Well, we would have to do this 10 times, one for each of the elements. But we could express it like this to say, do it in a matrix formation. So this is all, I've dropped the subscript because I mean this is a vector that contains all 10 nodes in level capital L, or 20 or 780 or ever how many there are. But this is all of them. This is a vector that contains all of those bias gradients. And the same thing here, A sub JL, well, this A that's all of the outputs of those nodes. And Y doesn't have a subscript, so that's all of the correct outputs, right? So if I were doing if I was doing our in this program, there would be 10 things here, there would be 10 activations, and there would be 10 correct answers, right? Because if I've got a 5, the first one will be 0, the second one will be 0, the third one will be 0. So it's like 0, 0, 0, 0, 0, 1, 0, 0, 0. It's just the one that's got a 5 that's lit up. But this represents that entire vector. And we noticed that we were multiplying times the derivative of the output function here. Well, this like a little O with a dot in the middle of it means multiply, but it means you're doing a matrix multiply. It's called the Hadamard product, and it would be taking, this would be generating, in case there were 10, this would be generating 10 different outputs, one for each node. So basically, it would be doing this, but this is for one node. This is for all 10 at the same time. And so, if you were using a tensor processing unit or a graphical processing unit, you would have a way of, or even if you were using NumPy or NumPy with Python, this is the way that you would express that equation, because you would be saying, I'm not going to index and sequentially go through these things. Here they are. Do them all in parallel. Okay? So the second equation, this gets a lot faster. The second equation is for intermediate layers, and we've already talked about this. This is where you take the weights, right? Stop it, Michael. or we take the weights, right? And so to get the bias gradient here, I have to take the weight times the bias gradient, the weight times the bias gradient, the weight times the bias gradient. And I pointed out that as we iterate through here, what we're really doing is, because we're iterating over the first subscript, which is the destination, right, not the source. The source is K, the destinations, right, that what we're really doing is we're going down a column of the weight matrix. So you can't multiply two columns together, right, because of the shape has to be right. So if you look real carefully, there's a little tiny T written right there. That means transpose, because we've got to take this weight vector and turn it on its side, because we're going a column at a time rather than a row at a time. And you can't do a column times a column, but if you take the column and you turn it into a row, which is what the transpose does, then the shapes will match so that you can do the multiplication. So essentially the error, this is again when you're taking everything all together, right? But we're going to be computing it where we're doing it one at a time, right? So we would work through, if we had a subscript of K, we would be going through all K of the nodes in a particular layer. And so when you're doing one of them, right, it's the weighted sum of the errors, right? And then times again, what was this? This is the derivative of the activation function. Well, that hasn't changed. It's still output times 1 minus the output. Okay? Now you do notice, you might say, you're using K's here, Mike, and you're using J's here. Why are you doing that? Well, I'm talking about the jth node here, and I'm talking about the kth node here. So that's why these are K's, because it's the output of this node. They were J's here because it was the output of this node. You might say, well, why didn't you use J instead of K? Because every time we've talked about the weight matrix, I used a JK, where J is the destination and K is the source, and I didn't want to flip that. And since I didn't want to flip that, I wanted to keep it the same the way it's always been. That meant that we're talking about the kth node here, where we were talking about the jth node here. Again, there are like a million little details like this. But if you think through the equation and you go back and you look at how I diagrammed what was going on here, and you look at, okay, here's an actual example, and here Mike broke it out into its parts. You've got every single step. I didn't leave out anything. So if you're a little fuzzy, you should be able to go back and unfuzzy yourself, because all of the details are there, okay? And the reason why I'm crawling through this, to some of you who are good at math, it might seem like we're crawling on our hands and knees over pebbles slowly. But I'm doing that because, A, I'm not good at math, so I have to have it laid out in excruciating detail, right? I say I'm not good at math. I taught myself all of this, right? But the point is, the way I teach myself is I have to go through every single step carefully. Because if I'm going to program it, you can't program it if you don't really know all of those steps, right? So that's why these notes are in such excruciating detail. And if you happen to be really good at math and there's just way too much detail here and you're a great programmer, I'm sorry, but I find the vast majority of students need this level of detail in order to be able to do the programming assignment. Okay, so that was that. The third equation hadn't changed. This just says, is just saying that the derivative of the cost function with respect to the biases, right, is just what we've been computing. So that's the bias gradient, okay? because that's what the bias gradient is. It's how rapidly the cost function is changing with respect to the bias, and that gives you how quickly the bias is changing, how quickly it's accelerating. And then the last equation is just what we've been talking about for a long time. It's just the output of the node times the error in the node that you're pointing to, and that's the weight gradient across JK. So the weight gradient, in other words, the gradient for the weight that goes to J from K, is the output of K times the error in node J. And that is how much I need to change, or the direction of change of that weight. Okay. All right. Questions about that? Let me stop for a second and ask. Are there questions about that? Everybody got it? That make me happy. It make me happy. Okay. Or nobody's asking questions because everybody's lost. You know, bored and lost look exactly the same thing from up here. Let's talk about backpropagation for the Rayleigh activation function. Okay. We talked about the sigmoid. It looks like an S. It varies from 0 to 1, very similar to the step function that we looked at for perceptrons. Another function, that's not the only function you could ever use for your output. There are lots of functions. Sigmoid is one of the most popular. Rayleigh is another very popular one. Rayleigh basically says, okay, the output of this function is going to be the maximum of 0 or the input. Which basically what that means is if your input is 0 or negative, so my input is negative here, right? The input's along the x-axis, the output's along the y-axis. So if my input is any negative value, then I just return a 0, right? Once I pass 0, my output will be equal to my input, okay? So Rayleigh of Z, we're still going to compute a Z, which is going to be the weighted sum of our inputs plus our biases, right? That'll still be the same Z that we were using before, but the Rayleigh of that is going to be max 0, comma Z, or you can write it as an if statement if you feel more computer science oriented. If the Z is less than or equal to 0, then the Rayleigh of the Z is 0. Otherwise, Z is going to be greater than 0, so the Rayleigh of Z is just going to be Z. Okay? Now, how does the Rayleigh affect our backpropagation equations? Well, it's going to simplify them. It's what it's going to do, because you'll remember, I just got through telling you that that when we compute these things, right, the first equation for the last layer is the derivative of the cost function with respect to the output of the node times the derivative of the activation function. Well, the derivative of the activation function for sigmoid was output times 1 minus the output, right? But what's the derivative of the Rayleigh going to be? Well, all the derivative is, remember, is the slope of the tangent line, okay? So what's the slope of this line at any point along this line? Now, it's flat. It has no slope. It's 0, okay? And then what's the slope of this line, right, at any point along this line? Well, it's just 1. So instead of the derivative being the output times 1 minus the output, the derivative is either going to be 0 if the input was less than or equal to 0, or the output, or the derivative will be 1 if the output was if the weighted sum of the inputs plus the biases are greater than 0. So I've got that written here. When Z is less than 0, and what is Z again? It's the weighted input. It's the weights times the inputs plus the biases. If that's less than 0, then the derivative of the ReLU is just going to be 0. Now, technically at 0, this puppy would be undefined at that one point. There is no slope at this inflection point, but we just say at 0, and that makes everybody happy. Okay. Question? Or we're clearing our throat. I think we're clearing our throat. Somebody's not on mute. And once you enter this range here, where the Z, the weighted sum of our inputs plus biases are greater than 1, well, the slope of this line is just 1, so the derivative is 1. So now what I do is I go back to the original equations that I just had, only instead of saying the derivative of the sigmoid, we have the derivative of our ReLU. Okay, so what does that do for us? Well, when Z is less than or equal to 0, the derivative here is going to be 0, so anything times 0 is going to be 0. So when Z is less than or equal to 0, our bias gradient for node J is going to be 0. When Z is greater than 0, it's simply going to be the output minus the desired output. Wait, Mike, where did that come from? That's just what we computed earlier, right? That's the derivative of the cost function time with respect to the output. So basically, it's this times 0, which gives us 0 if Z is less than 0. And this is a 1 otherwise, so I didn't put the 0, I didn't put the 1 here, but you could say times 1 if that made you happy. It's not going to change anything. So this is what our equations have simplified to. How about the intermediate layer? Well, you still have the weighted sum of the errors, right, of the biases, just like before, right? But now instead of the derivative of the sigmoid, we have the derivative of the ReLU, which again is either going to be 0 or 1. So if it's 0, then this whole thing doesn't matter what any of this is you're going to get a 0, right? And if Z is greater than 0, well, then it's just going to be this first part, which is, if you're doing it one at a time, right, is the weighted sum of the errors. So again, what vanished here is you no longer have the times the output times 1 minus the output, because that part was the derivative of the sigmoid function. We don't have a sigmoid now, we have a ReLU, and when it's positive, it just becomes 1. So that part of the equation vanishes. There's no change there. And the third equation, or the fourth if you're keeping this in, which I'm keeping it in because Nelson wrote it that way, is still just this doesn't the backpropagation equation for weight doesn't refer to the derivative of the output function, so that's why this equation didn't change. It's still the weight gradient 2J from K is the output of K times the error in J. That's all it is. And we can summarize this by saying, okay, if you've got a sigmoid, it's the derivative of the cost function with respect to the output times output times 1 minus the output if it's sigmoid, or it would be times 1 here. You don't have to write the 1 when A is greater than 0. It would have been this times 0 when the output is less than or equal to 0, so I just put a 0 here. And you might notice a slight change here. I didn't say when Z is greater than 0, I said when the output is greater than 0. And the reason I did that is if you go back and you look at the equations, right, when the Z is greater than 0, then when the Z is greater than 0, then the ReLU itself is going to be greater than 0. When the Z is less than 0, the ReLU is going to be exactly 0. And so I just said, rather than worrying about Z, keeping up with that separately, just use the activation A. So this is Z having gone through the ReLU function, which means if Z is greater than 0, then the ReLU function just passes that Z as the output. It becomes the A. So refer to A here. And if the Z were less than 0, well, then the A is going to be 0. Right? So you don't have to worry about keeping up with Z, the weighted sum of the inputs plus the biases separately. You can just use the activation that you already have stored in your matrices. And I do the same thing here on this one. So this was the equation for the final layer, the equation for the hidden layers. Again, you can see that all that changes is this gets swapped out for a 1, which I don't even write down, when the output's greater than 0. This gets swapped out for a 0 when the output is less than or equal to 0. And so because this would be swapped out for a 0, this whole thing goes to 0 here. And again, calculating the weight gradient doesn't change at all. Okay. Questions about that for me? Any questions about that? So what have I done now? I've not only shown you the equations for the sigmoid neuron, the backpropagation equations for sigmoids. I have gone through and showed you the math of where they come from. They basically depend on the derivative of the output function, right? Which is either sigmoid or now we've introduced ReLU, and I've showed you how those two activation functions cause the backpropagation equations to change slightly because the first two use the derivative of the output function. Okay. Let's see what we wanted to do next. Next, what I want to do is I want to show you, I'll take up pretty much the rest of the class, 2 videos that go through backpropagation in detail, okay? And we'll show you the, we'll pretty much try to go through the calculus, explaining at a more detailed level where these things come from, right? Or more like okay, what's the theory behind why these things work? So I'm using 3 blue, 1 brown, which I find is quite good. So there are 2 of them. They're each about 10 minutes apiece. So let's watch them.
Here we tackle backpropagation, the core algorithm behind how neural networks learn. After a quick recap for where we are, the first thing we'll do is an intuitive walkthrough for what the algorithm is actually doing, without any reference to the formula. Then, for those of you who do want to dive into the math, the next video goes into the calculus underlying all this. If you watched the last 2 videos, or if you're just jumping in with the appropriate background, you know what a neural network is and how it feeds forward information. Here we're doing the classic example of recognizing handwritten digits, whose pixel values get fed into the first layer of the network with 784 neurons. And I've been showing a network with 2 hidden layers having just 16 neurons each, and an output layer of 10 neurons, indicating which digit the network is choosing as its answer. I'm also expecting you to understand gradient descent, as described in the last video, and how what we mean by learning is that we want to find which weights and biases minimize a certain cost function. As a quick reminder, for the cost of a single training example, what you do is take the output that the network gives, along with the output that you wanted it to give, and you just add up the squares of the differences between each component. Doing this for all of your tens of thousands of training examples and averaging the results, this gives you the total cost of the network. And as if that's not enough to think about, as described in the last video, the thing that we're looking for is the negative gradient of this cost function, which tells you how you need to change all of the weights and biases, all of these connections, so as to most efficiently decrease the cost. Backpropagation, the topic of this video, is an algorithm for computing that crazy complicated gradient. And the one idea from the last video that I really want you to hold firmly in your mind right now is because thinking of the gradient vector as a direction in 13,000 dimensions is, to put it lightly, beyond the scope of our imagination, there's another way you can think about it. The magnitude of each component here is telling you how sensitive the cost function is to weight and bias. For example, let's say you go through the process I'm about to describe and you compute the negative gradient, and the component associated with the weight on this edge here comes out to be 3.2, while the component associated with this edge here comes out at 0.1. The way you would interpret that is that the cost of the function is 32 times more sensitive to changes in that first weight. So if you were to wiggle that value just a little bit, it's going to cause some change to the cost. And that change is 32 times greater than what the same wiggle to that second weight would give. Personally, when I was first learning about backpropagation, I think the most confusing aspect was just the notation and the index chasing of it all. But once you unwrap what each part of this algorithm is really doing, each individual effect that it's having is actually pretty intuitive. It's just that there's a lot of little adjustments getting layered on top of each other. So I'm going to start things off here with a complete disregard for the notation and just step through those effects that each training example is having on the weights and bias. Because the cost function involves averaging a certain cost per example over all the tens of thousands of training examples, the way that we adjust the weights and biases for a single gradient descent step also depends on every single example. Or rather, in principle it should, but for computational efficiency, we're going to do a little trick later to keep you from needing to hit every single example for every single step. In either case, right now, all we're going to do is focus our attention on one single example, this image of a tube. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random. Maybe something like 0.5, 0.8, 0.2, on and on. And we can't directly change those activations. We only have influence on the weights and biases. But it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we wanted to classify the image as a tube, we want that third value to get nudged up, while all of the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase to that number 2 neuron's activation is in a sense more important than the decrease to the number 8 neuron, which is already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer, plus a bias, which has all been plugged into something like the sigmoid squishification function, or a ReLU. So there are 3 different avenues that can team up together to help increase that activation. You can increase the bias, you can increase the weights, and you can change the activations from the previous layer. Focusing just on how the weights should be adjusted, notice how the weights actually have differing levels of influence. The connections with the brightest neurons from the preceding layer have the biggest effect, since those weights are multiplied by larger activation values. So if you were to increase one of those weights, it actually has a stronger influence on the ultimate cost function than increasing the weights of connections with dimmer neurons, at least as far as this one training example is concerned. Remember, when we talk about gradient descent, we don't just care about whether each component should get nudged up or down. We care about which ones give you the most bang for your buck. This, by the way, is at least somewhat reminiscent of a theory in neuroscience for how biological networks of neurons learn, Hebbian theory, often summed up in the phrase, neurons that fire together wire together. Here, the biggest increases to weights, the biggest strengthening of connections, happens between neurons which are the most active and the ones which we wish to become more active. In a sense, the neurons that are firing while seeing a tube get more strongly linked to those firing when thinking about it too. To be clear, I really am not in a position to make statements one way or another about whether artificial networks of neurons behave anything like biological brains, and this fires together, wire together idea comes with a couple meaningful aspects. But taken as a very loose analogy, I do find it interesting to note. Anyway, the third way that we can help increase this neuron's activation is by changing all the activations in the previous layer. Namely, if everything connected to that digit 2 neuron with a positive weight got brighter, and if everything connected with a negative weight got dimmer, then that digit 2 neuron would become more active. And similar to the weight changes, you're going to get the most bang for your buck by seeking changes that are proportional to the size of the corresponding weights. Now, of course, we cannot directly influence those activations. We only have control over the weights and biases. But just as with the last layer, it's helpful to just keep a note of what those desired changes are. So keep in mind, zooming out one step here, this is only what that digit 2 output neuron wants. Remember, we also want all of the other neurons in the last layer to become less active. And each of those other output neurons has its own thoughts about what should happen to that second to last layer. So, the desire of this digit 2 neuron is added together with the desires of all the other output neurons for what should happen to this second to last layer. Again, in proportion to the corresponding weight, and in proportion to how much each of those neurons needs to change. This right here is where the idea of propagating backwards comes in. By adding together all these desired effects, you basically get a list of nudges that you want to happen to the second to last layer. And once you have those, you can recursively apply the same process to the relevant weights and biases that determine those values, repeating the same process I just walked through and moving backwards through the network. And zooming out a bit further, remember that this is all just how a single training example wishes to nudge each one of those weights and biases. If we only listened to what that 2 wanted, the network would ultimately be incentivized just to classify all images as a 2. So what you do is you go through this same backprop routine for every other training example, recording how each of them would like to change the weights and the biases. And you average together those desired changes. This collection here of the averaged nudges to each weight and bias is, loosely speaking, the negative gradient of the cost function referenced in the last video, or at least something proportional to it. I say loosely speaking only because I have yet to get quantitatively precise about those nudges. But if you understood every change that I just referenced, why some are proportionally bigger than others, and how they all need to be added together, you understand the mechanics for what backpropagation is actually doing. By the way, in practice, it takes computers an extremely long time to add up the influence of every single training example, every single gradient descent step. So here's what's commonly done instead. You randomly shuffle your training data and then divide it into a whole bunch of mini batches, let's say each one having 100 training examples. Then you compute a step according to the mini batch. It's not going to be the actual gradient of the cost function, which depends on all of the training data, not this tiny subset. So it's not the most efficient step downhill. But each mini batch does give you a pretty good approximation. And more importantly, it gives you a significant computational speedup. If you were to plot the trajectory of your network under the relevant cost surface, it would be a little more like a drunk man stumbling aimlessly down a hill, but taking quick steps, rather than a carefully calculating man determining the exact downhill direction of each step before taking a very slow and careful step in that direction. This technique is referred to as stochastic gradient descent. There's kind of a lot going on here, so let's just sum it up for ourselves, shall we? Backpropagation is the algorithm for determining how a single training example would like to nudge the weights and biases, not just in terms of whether they should go up or down, but in terms of what relative proportions to those changes cause the most rapid decrease to the cost. A true gradient descent step would involve doing this for all your tens of thousands of training examples and averaging the desired changes that you get. But that's computationally slow. So instead, you randomly subdivide the data into these mini batches and compute each step with respect to a mini batch, repeatedly going through all of the mini batches and making these adjustments, you will converge towards a local minimum of the cost function, which is to say your network is going to end up doing a really good job on the training examples. So with all of that said, every line of code that would go into implementing backprop actually corresponds with something that you have now seen, at least in informal terms. But sometimes knowing what the map does is only half the battle. Just representing the damn thing is where it gets all muddled and confusing. So, for those of you who do want to go deeper, the next video goes through the same ideas that were just presented here, but in terms of the underlying calculus, which should hopefully make it a little more familiar as you see the topic in other resources. Before that, one thing worth emphasizing is that for this algorithm to work, and this goes for all sorts of machine learning beyond just neural networks, you need a lot of training data. In our case, one thing that makes handwritten digits such a nice example is that there exists the MNIST database with so many examples that have been labeled by humans. So a common challenge that those of you working in machine learning will be familiar with is just getting the labeled training data that you actually need.
So that was the first one. Let's now move over to the one that gets into the calculus.
The hard assumption here is that you've watched part 3, giving an intuitive walkthrough of the backpropagation algorithm. Here, we get a little bit more formal and dive into the relevant calculus. It's normal for this to be at least a little confusing, so the mantra to regularly pause and ponder certainly applies as much here as anywhere else. Our main goal is to show how people in machine learning commonly think about the chain rule from calculus in the context of network, which has kind of a different feel from how most introductory calculus courses approach the subject. For those of you uncomfortable with the relevant calculus, I do have a whole series on the topic. Let's just start off with an extremely simple network, one where each layer has a single neuron in it. So this particular network is determined by 3 weights and 3 biases. And our goal is to understand how sensitive the cost function is to these variables. That way we know which adjustments to those terms is going to cause the most efficient decrease to the cost function. And we're just going to focus on the connection between the last 2 neurons. Let's label the activation of that last neuron with a superscript L, indicating which layer it's in. So the activation of the previous neuron is a L minus 1. These are not exponents, they're just a way of indexing what we're talking about, since I want to save subscripts for different indices later on. Now let's say that the value we want this last activation to be, for a given training example, is Y. For example, Y might be 0 or 1. So the cost of this simple network for a single training example is AL minus Y squared. We'll denote the cost of that one training example as T0. As a reminder, this last activation is determined by a weight, which I'm going to call WL, times the previous neuron's activation plus some bias, which I'll call VL. And then you pump that through some special nonlinear function like the sigmoid or a radian. It's actually going to make things easier for us if we give a special name to this weighted sum, like V, with the same superscript as the relevant activation. This is a lot of terms, and a way that you might conceptualize it is that the weight, the previous action, and the bias all together are used to compute V, which in turn lets us compute A, which finally, along with the constant Y, lets us compute the cost. And of course, AL minus 1 is influenced by its own weight and bias and such. But we're not going to focus on that right now. Now, all of these are just numbers, right? And it can be nice to think of each one as having its own little number line. Our first goal is to understand how sensitive the cost function is to small changes in our weight, WL. Or phrased differently, what is the derivative of C with respect to WL? When you see this del W term, think of it as meaning some tiny nudge to W, like a change by 0.01. And think of this del C term as meaning whatever the resulting nudge to the cost is. What we want is their ratio. Conceptually, this tiny nudge to WL causes some nudge to ZL, which in turn causes some nudge to AL, which directly influences the cost. So we break things up by first looking at the ratio of a tiny change to ZL to this tiny change W. That is, the derivative of ZL with respect to WL. Likewise, you then consider the ratio of the change to AL to the tiny change in ZL to cause it. As well as the ratio between the final nudge to C and this intermediate nudge to AL. This right here is the chain rule, where multiplying together these three ratios gives us the sensitivity of C to small changes in WL. So on screen right now, there's kind of a lot of symbols. And take a moment to just make sure it's clear what they all are. Because now we're going to compute the relevant derivative. The derivative of C with respect to AL works out to be 2 times AL minus Y. Notice, this means that its size is proportional to the difference between the network's output and the thing that we want it to be. So if that output was very different, even slight changes stand to have a big impact on the final cost function. The derivative of AL with respect to ZL is just the derivative of our sigmoid function, or whatever nonlinearity you choose to use. And the derivative of ZL with respect to WL, in this case, comes out just to be AL minus 1. Now, I don't know about you, but I think it's easy to get stuck head down in the formulas without taking a moment to sit back and remind yourself of what they all actually mean. In the case of this last derivative, the amount that small nudge to the weight influenced the last layer depends on how strong the previous neuron is. Remember, this is where that neurons that fire together wire together idea comes in. And all of this is the derivative with respect to WL only of the cost for a specific single training example. Since the full cost function involves averaging together all those costs across many different training examples, its derivative requires averaging this expression that we found over all training examples. And of course, that is just one component of the gradient vector, which itself is built up from the partial derivatives of the cost function with respect to all those weights and biases. But even though that's just one of the many partial derivatives, it's more than 50% of the work. The sensitivity to the bias, for example, is almost identical. We just need to change out this del Z del W term for a del Z del B. And if you look at the relevant formula, that derivative comes out to be 1. Also, and this is where the idea of propagating backwards comes in, you can see how sensitive this cost function is to the activation of the previous layer. Namely, this initial derivative in the chain rule expression, the sensitivity of Z to the previous activation comes out to be the weight, WL. And again, even though we're not going to be able to directly influence that previous layer activation, it's helpful to keep track of, because now we can just keep iterating the same chain rule idea backwards to see how sensitive the cost function is to previous weights and previous biases. And you might think that this is an overly simple example, since all layers just have one neuron, and that things are going to get exponentially more complicated for a real network. But honestly, not that much changes when we give the layers multiple neurons. Really, it's just a few more indices to keep track of. Rather than the activation of a given layer simply being AL, it's also going to have a subscript indicating which neuron of that layer it is. Let's go ahead and use the letter K to index the layer L minus 1, and J to index the layer L. For the costs, again, we look at what the desired output is, but this time we add up the squares of the differences between these last layer activations and the desired output. That is, you take a sum over ALJ minus YJ squared. Since there's a lot more weights, each one has to have a couple more indices to keep track of where it is. So let's call the weight of the edge connecting this kth neuron to the jth neuron WLJK. Those indices might feel a little backwards at first, but it lines up with how you'd index the weight matrix that I talked about in the part 1 video. Just as before, it's still nice to give a name to the relevant weighted sum, like Z, so that the activation of the last layer is just your special function, like the sigmoid, applied to Z. You can kind of see what I mean, right? Where all of these are essentially the same equations that we had before in the one neuron per layer case. It's just that it looks a little more complicated. And indeed, the chain rule derivative expression describing how sensitive the cost is to a specific weight looks essentially the same. I'll leave it to you to pause and think about each of those terms if you want. What does change here, though, is the derivative of the cost with respect to one of the activations in the layer L minus 1. In this case, the difference is that the neuron influences the cost function through multiple different paths. That is, on the one hand, it influences AL0, which plays a role in the cost function, but it also has an influence on AL1, which also plays a role in the cost function. And you have to add those up. And that, well, that's pretty much it. Once you know how sensitive the cost function is to the activations in this second to last layer, you just repeat the process for all the weights and biases feeding into that layer. So pat yourself on the back. If all of this makes sense, you have now looked deep into the heart of backpropagation, the workhorse behind how neural networks learn. These chain rule expressions give you the derivatives that determine each component in the gradient that helps minimize the cost of the network by repeatedly stepping downhill. If you sit back and think about all that, this is a lot of layers of complexity to wrap your mind around. So don't worry if it takes time for your mind to digest it.
Okay. So like I said, that's probably a much better example than I would be able to give you guys by having all of the diagrams there. A few things. Our exam is going to be on Tuesday. The notes that I'm going to publish, I published the notes already, but after, because I don't know how far we're going to get, I'll go back after and re-edit the notes, taking out what we didn't cover. So we didn't get to the TANH function or a couple of other little things that I wanted to cover. One thing that I'm going to leave in the notes that I am not going to cover is the Python implementation. The Python implementation of the program will be in the notes. I have some introductory notes before that describe this program that's in chapter 1 or 2 of Nielsen's book. But I used to go through this in detail, and I've decided that it probably does more harm than good because it's written in very dense Python that is highly dependent on matrix calculation using the NumPy or NumPy, however you pronounce it, library. So it's all there. The comments in dark black are comments that I've made to kind of add to the comments that he had that help you understand what's going on. And after all of that, I have a clean version of the program that I give in the notes. All of this is in chapter 1 or 2 of Nielsen. So you're welcome to go through it. It might help you. It might hurt you. I don't know, because it is a very different way of writing the program than what you're going to be doing. But I did want you to know it's in the notes. It's there so that you can look at it. Any questions for me? Okay, what I'm going to do is we're already 2 minutes over time, so I'm going to stop today's lecture. But if you have any questions, I'll be happy to answer them after class. And again, I'll see. Well, I won't necessarily see you, but you'll meet together in person for the exam on Tuesday. Okay.